Oh. Okay, last time we do this problem by two methods. First, by using a simple Newton's law, and then the second way is to use momentum. Now, the solution for it is this. If we use the normal Newton's law, we know the initial velocity of the balls to be 10 meters per second, which is around 36 kilometers per hour. A little bit slow if you're talking about the shooting speed of the football. Some people can shoot at the speed of more than 100 kilometers per hour. The velocity of the ball at the end is 0 meters per second, and the mass is 0.5 kilograms. So the total time it took to stop is 0.5 seconds. So according to motion, acceleration is the rate of change in, this is an average acceleration. So it's the final velocity minus initial velocity divided the time. And it is 0 minus 10 divided by 0.5. So the acceleration is 20 meters per second. Okay, minus 20 meters per second. And the minus suggests that the opposite direction to the initial velocity. Now we get Newton's second law, F equal to ma, and then you times the mass to the acceleration, and 20 times 0.5, so you add around 10 newtons, which is equal to the weight of 1 kilogram object. So it's not that hard to stop. Now, if we look at it in terms of momentums, we first find initial momentum. The momentum initial is 0.5 times 10 meters per second, and that is 5 kilogram meters per second. And final momentum is 0 because the ball stopped. So by definition of force equal to the change in momentum over time, or the rate of change of momentum, you get that Pf minus Pi over delta T, or 0 minus 5 over 0.5. Then the answer is also 10 newtons. So it's simpler in a way and shorter in order to work. So let's check in for another two examples. And I hope you enjoy some anime to this. This is recording by some of the Premier League. I'm not sure who that person was, but the fastest speed of the shooting of the football is 60 meters per second. Well, it is quite unbelievable because you see 30 meters per second is 108 kilometers per hour. So he shoot at 60 meters per second, then that means the ball is traveling at almost 200 kilometers per hour. Okay, but that's true according to research from Google. If the mass of a football is 0.5 kilograms, find the force acting on the football if the contact time is 0.02 seconds, or what we call 20 milliseconds. That, remember last time I said that 0.5 is a little bit too long. Well, actual contact times between two objects when they collide is around 20 milliseconds. the harder the surface, the shorter the contact times. For example, in tennis, the harder you, the tighter you strung the tennis string, the shorter the contact time is, and the shorter the contact time, the more force you can have on the ball. So professional player in tennis strung their racket string at almost twice the strength for ordinary player. Okay, so let's take a look at this. If the velocity is 60 meters per second, okay, and let's say that it starts from 0. So if you want to kick the ball to have a speed at the end of 60 meters per second, what is the force that you're acting on the ball? So initial momentum is 0 kilogram meters per second because we assume that the ball will start from 0. And then the final momentum will be 0.5 times 60 meters per second. And that is 30 kilogram meters per second. So the force acting on the ball is delta P by delta T. And you have PF minus PI over delta T. And it is 30 minus 0 over 0.02. And that means that he have to kick it with 1,500 newtons force. Okay. And that means the foot have to travel a little bit fast in order to hit that ball. Okay. We can count. We can think that it's like an elastic collision, but let's work on that later on. Now, there is another way of shooting a ball that much quicker. It's called a reverse cannon shoot. Possibly you saw this in anime called Tsubasa, but it actually worked. If you look at the soccer match, clearly sometimes the shoot is begin with the passing backward. So one of the player passing the ball backward, and then the other one will run in and charge it and kick it, including the momentum of the whole body to that ball. Now, because the ball have initial velocity in the opposite direction as of the shooter, the speed of the ball increase a lot. Okay. So let's assume that if the initial velocity is 20 meters per second, okay, backward, so it's minus 20, and then you kick it and then make it plus 20 meters per second. And 20 meters per second is roughly 72 kilometers per hour. And the mass of the ball is still 0.5 kilograms. You see that the initial momentum is m times u, or 0.5 times minus 20. So it's minus 10 kilogram meters per second. And then the final momentum is mv, so it's plus 0.5 times 20. So it's plus 10 meters per second. So the force that acting is 10 minus by minus 10, and divided by 0.02, and that gives you 1,000 newtons to kick the ball. Okay, and that is one particular way of doing a kick, reverse cannon kick. Let's take a look at another question. And this is, I got these ideas from a movie called Concussion, and which I suggest that if you like Will Smith, possibly this is one of his best acting skills. It's not a action movie, so it is quite a drama movie. The Concussion movies is about the brain injuries in American football player when they having a small, when they play the football and then their head clash into each other and causing small injuries at a time. But after a few years, that injuries add up. And at the end, when they getting older, they have a brain injuries that are a brain dysfunction that usually cause them to death. So, Will Smith playing a forensic doctors who found out this problem in American football player. And he spent a lot of times and energy try to prove it. Well, with an obstacle or from many of the NFL NFL official, to claim that his work is invalid and is not on the scientific ground. But eventually it proved true, and right now, if you're looking at American football, they have a CT scan right beside the field. Whenever the player get injured, get hit in the head, they have to doing the CT scan right away to make sure that this problem doesn't fit. And that's one of the reasons that the major boxing player right now don't wear a helmet, because eventually they prove that the helmet is the one that causing more damage because they have more mass. Adding the mass to the head, then when you hit the boxer in the head twists with more torque. So eventually right now the boxing competition doesn't involve any headgear. And if you are under the age of, I believe it's 15, you're not allowed to box. And if you are under 20, you can box, but you cannot hit another people on the face or on the head. I read an article says that the Premier League in Britain, United Kingdom, considering banning the use of the head in not a professional football, because the professional football you get paid for that, you know the risk. But in educational football in schools and in university, they considering banning the use of the head because it causes more damage than just kicking or playing with your other organs. Now, in this problem, we will consider that first, if the ball can move with a speed of 30 meters per second, and that is around 108 kilometers per hour, and then you use your head to shoot. Okay, if it head-on collision, the ball coming in at 30 meters per second and bounce back at also 30 meters per second, find the force on the head, and given that the football mass is roughly 0.5 kilograms and the contact time is 0.02 seconds, what would happen to the head? And you will see that from force equal to the rate of change of momentum, delta P over delta T, is PF minus PI over delta T. So it's 0.5 times 30 minus 0.5 times minus 30 divided by 0.02. And the force is 15 minus by minus 15 divided by 0.02. Up there, the negative and negative making positive. So it is add up to be 30. And then 0 divided by 0.02. And that is 3,000 divided by 2, or 1,500 newtons on the football. And because it is action and reaction, the same force is acting on the head. And you see, the force that acting on the head is like the weight of a two-person. 1,500 newtons equal to the weight of the mass 20 of the mass of 150 kilograms that getting act on your head. Now, well, let me explain why that is so serious. Our head is not a solid object. It is a solid, but inside it is a liquid, and you have your brain floating inside that liquid with a tiny space between the brain surface to the skull. That surface is very less than 0.5 centimeters. Now, if you're checking your brain with a lot of force, and then you check your head, your brain will just checking back and forth according to the force that happens. And if it's so hard, the surface of the brain will hit to the back of the bones, and that causes bruises on the brain. And that if that force is large enough, bruises and bleeding will appear on your brain surface. And once the bleeding starts, it will cause a damage to the tissue, to the brain tissue. Okay. If the force is large enough, it can damage the brain tissue right away. But if the force is not large, we call it a concussion. You might feel dizzy for a while, but then the bruise on the brain will react to that, because every time we have some injuries, our body will automatically add some proteins to strengthen that surface. Now, when the body starts to make a protein inside the brain, it's not helping, but it's actually damaging, because it's causing a called the ganglia. So a region of the protein that is not needed in the brain. And eventually this protein will cause the brain to function differently and improperly. So it leads to many other disease and many others situations. And that's, well, you possibly need to look at it. Well, because your friend asked, might not be understanding this correctly, but if wearing helmet is dangerous for concussion, why do we wear helmets or other activities for motorcycle? Well, it is a different kind of motion that happens. In boxing, the force is coming from the side. And then when you hit some people on the side, it is causing a twist on the twist on your head. And then it causes damage to your spine and the base of your skull. But the helmet for motorcycle and other activities is not protecting against the twist of the head, but is protecting about the force that coming directly to your head. It is for different activities. Okay. In motorcycle, if you're getting, well, fall down and your head hit the ground, it's not a twisting motion. It is usually a contact direct on the straight line. So that in that case, the helmet helps. But the twist is the one they're worried about in boxing. If, well, that is one of the problem. If the motorcycle helmet, if you're wearing a full motorcycle helmet and then you attach it to your head correctly, it will reduce twisting motion a little bit. Well, it still have the chance of injuries in the twisting motion, but it will greatly reduce injuries on the blunt force that coming directly. Okay. Okay. Now let's go to a concept of collision. And that is the case of the two objects collide to each other. And actually this is the perfect opportunity to discuss the accident of Dr. Katai. She was hit by a big bike, including the biker, and the mass that collide on her is, well, I believe twice or even more than her mass. So the bike and the bicycle and the policeman is traveling at 80 kilometers per hour upon collision. Well, I know you read the news and it said 108, but the actual speed when hit is about 80s. So that is a lot of momentum. And then when collided to a mass that is smaller by half, okay, it will result in one mass, the body is to flying backward in very great velocity. And actually that collision is two-dimensional because the Dr. Katai is moving across the street, but the cars is coming along the streets. So we are talking at two-dimensional collision momentum at this point. So let's get to the basic concept first. This is a discussion on Newton's third law, and it's action equal to reaction. And then when you have two objects collide, okay, it will having force acting on each other. Well, when we say collision, it doesn't mean that the two objects have to touch each other. Sometimes it doesn't touch. For example, a gas molecules collide to another gas molecules. It is getting closer until the repulsive force, actually the electric force repulsing to each other, causing a force that appears only when the two things get closer to each other. So when the object have a contact, okay, means that it is getting closer until the surface can have the force acting to each other. You have action and reaction force. I call this two things. F21 is the force that two acting on one, and F12 is the force that one acting on two. Okay, it might confusing you if you read some other books and then they using a different notation. Sometimes they using F21 is the force that one acting on two, and F12 is force that two acting on one. So that depends. But in this case, F21 is two acting on one. And this force have to be equal and opposite to each other. So according to Newton's law, this is these two things. So after the contact times, the two objects will move in different velocity and different direction. So if one coming in with this U1 in this case, and the force is acting to the left, so the initial, this is also delta V. Okay, so a final velocity would be something like that to the left. And for this case, something like this to the right. So M1 and M2 are different way. Now, if we take a look, starting from Newton's third law, we said F12 equal to minus F21. And using a definition that the force is mass times the change, is a change in momentum, or the mass times change time acceleration. So M2 equal to F12 is equal to M2, one acting on two, times the change in velocity, so that's V2 minus U2 over delta T, and equal to minus M1 V1 minus U1 over delta T. And because the contact time is equal, you can cancel the contact times out. So what you have left is M2 V2 minus M2 U2 equal to minus M1 V1 minus M1 U1. And you pull the V's on the same side and the U's on the same side. We see that M1 V1 plus M2 V2 equal to M1 U1 plus M2 U2. And that's the final momentum. Final total momentum is equal to initial momentum. And this means that the momentum is constant. Okay. So during collision, the total momentum is always constant. For example, the case of Dr. Gatai, the bicycle with the mass of roughly 150 kilograms or to 200 kilograms is traveling at 80 kilometers per second per hour, is around 20 something, so 25 meters per second. And then collided with another object, which is maybe half the mass. And along the road, well, she's crossing the road. This means that the velocity along the road is 0. So because the momentum is conserved, and if the bike is almost stopped after the collision, she's traveling at, let's say, twice the speed of the bike along the direction of the road, according to conservation of momentum. And if you watch the clip, you see that she's traveling quite far from the place that were hit. And you see that in many motorcycle accidents. Actually, I have a chance to see another one a few days ago also. So in collision, according to Newton's third law, momentum is always constant. But then if we take a look at energy, okay, I'll just saying some things about energy right now. We doesn't have a chance to prove it. Actually, the next chapter will be about work and energy. So let me bring it on and use it right here first. A kinetic energy of an object can be defined by using the formulas 1/2 mv squared. This is a definition of the energy. And the kinetic energy of the system is 1/2 mv squared m1v1 squared plus 1/2 m2v2 squared. Now, if it also conserved, it means that the energy is not changing to something else. The initial energy and the final energy must be equal, and we call this type of collision that an elastic collision. Elastic collision is a collision that both momentum and energy are conserved. Now, if the sorry, if the energy is not conserved, means that the energy is changing into some other form. For example, the sound, the heat, or breaking of someone's bones or something else. The initial energy must be greater than final energies, and this is called a inelastic collision. Now, most of the time, the collision is inelastic, but there are some cases where you have an elastic collision, especially when you don't have any other forces involved. So let's take a look at some example Many of you might notice this. This is from an actual accident that happens almost 10 years ago on the expressway above the BSAC University. Okay, but I changed it a little bit, so you might not notice a car. Well, to be clear, it is a white Honda Civic driving at 60 meters per second. So it's all around 215 kilometers per hour. Collided a van which moved at 30 meters per second. The van is moving at around 108 kilometers per hour. And then they moving together after collision. Okay. What is the speed of both vehicles after collision, giving mass? A given mass of the cars is around 800 kilograms, and mass of the van is 1,200 kilograms. Okay. 800 kilograms is roughly a mass of a sedan cars. The mass of the van of 1,200 kilograms is a little bit low, actually, with a lot of people on it, but let's assume that it is that case. So you see that the mass of the car is 60 meters per second and the van is 30 meters per second. And M1 is 800 kilograms and M2 is 1,200 kilograms. And they collided, and then assuming that they stuck in together and with some velocity, we get that the initial momentum is equal to the summation of the final momentums. So the initial M1 plus U1 times U1 plus M2 times U2 equal to M1 plus M2 times V. And we see that 800 kilograms times 60 meters per second plus 1,200 kilograms times 30 meters per second equal to 2,000 times V. The two masses together is 2,000. So eventually this is 48 plus 36 equal to 2V. We cancel the zeros here. And it gets 84 equal to 2, and the velocity is 84 divided by 2, or 42 meters per second. Now here's the thing. The van is usually travel at 108 kilometers per hour. But after the collision, it's moving forward with velocity increasing to 42 meters per hour, meters per second. So that's roughly 30 kilometers more, 36 kilometers per hour more. So it is to about 140 kilometers per hour in a very short time, around maybe less than 1 second that it's moved back. So for the person in the van, they have been jolted forward, okay, from their seat. And you see that many of the people flying backwards, according to that, because they don't have any seat belts on in the van. So in this case, well, the actual accident, the van lose control after it was hit in the back and sending it travel forward with higher speed and then collided to the ramp on the side and then, well, flipped, launching some of their passenger on the back, flying through the rear window and then falling down the expressway, and then, well, they pass away after that. I think there are 3 bodies that was shot out from the back and then died. The driver of the van died, well, immediately when hitting the ramp of the expressway. The only person that survived is the one that sitting right behind the driver, because they are at the center of gravity of the van. So that is the safest point to be. Okay. You possibly can Google search this accident also. So let's take a look at is this things elastic or inelastic collision. The initial energy is 1/2 m1u1 square plus 1/2 m2u2 square, and that is 1/2 of 800 times 60 square plus 1/2 of 1200 times 30 square. So you get to cancel to 8, you get 400. Many of you may wonder why I say 1200 instead of 1200. It's got, well, I'm studying from United States. Sometimes the people in the US don't use 1000. If it's not that much, they will use 1200 instead. Okay. Unless you have more than 100, so it's 10,000 that they will use 1000. Okay. And sometimes they use grand instead of 1000, especially for money. Okay, working on that, you get 60 squared is 36 times 100. So 36 times 4 times 10 to the 100 times 100. So 10 to the power of 4. Plus 6 times 9 times 10 to the 4. So you got 36 times 4 is 144 plus 6 times 9 is 54. So it's 198 times 10 to the 4, or 1980 kilojoules of initial energy. Now, final energy is 1/2 of the total mass times the velocity, final velocity. So you said 1/2 of 2000 times 42 squared. Using the calculator, you got 1.764 times 10 to the 6 joules, or you see that initial energy is 1.98 and final energy is 1.76 megajoules. So you lost energy at around 0.216 times 10 to the 6, or 0.2 megajoules. And that loss is going to another form of energy, maybe a sound crumbling of the object, and that's the energy loss. And this is collision is called inelastic collision. Okay. So most collision is inelastic, especially when you take a look when you are at real life situation. But sometimes you have an elastic collision. For example, in the pool table, it's almost inelastic. Okay, but for something like the collision between stars or the with the spring involved, you can set a system that is almost elastic collision. So if we're doing an elastic collision in one dimension, what will happen? Well, we have a case where it's inelastic because it's collide to each other. But let's assume that it's not connect to each other after collision. So if we have M1 is traveling at U1 meters per second collide to M2, which is at rest, before collision. And then this is in one dimension, so I'm not worried about the other axis. So after the collision, assuming that the second mass is moving forward with its velocity to be v2. And by intuition, you got something coming in and then colliding to something that is at rest. And then afterward, the thing that used to be at rest is moving forward. Now the things that coming in should be moving slower than it used to be. So we're assuming that it's moving with velocity v1 after the collision. And assuming that this two doesn't lose energy to any other form. So it can happen if you attach a spring in here. So the spring will convert the energy in form into the elastic energy and then release it. And the total energy is remain constant. So you can have an elastic collision after this. So if the energy is also conserved, we can set up an equation from these two conditions. So the conservation of momentum m1 u1 plus m2 times 0, this is 0 because it's at rest, equal to m1 v1 plus m2 v2. So let me explain this. I'm going to prove the case where m2 is at rest first. And if you're interested, you can prove it with the same method by using that M2 is traveling at some speed to the right. And you will end up with some complete form of this equation. But I will leave you for you to do that. So if the momentum conserved, this is 0. So I move everything that have a subscript 1 on one side and subscript 2 on the other side. So I get m1 times u1 minus v1 equal to m2 times v2. This is the first equation. Now, for the conservation of energy, initial energy is 1/2 m1 u1 square equal to 1/2 m1 v1 square plus 1/2 m2 v2 square. Well, the 1/2 cancel each other out, and doing the same thing, moving the 1 on one side and the 2 on the other side. We get m1 u1 square minus v1 square equal to m2 v2 square. And because it is one dimension, you can dropping the vector sign on the first equation. And the second equation, you can break it up because u1 square minus v1 square is like a y square minus x square. You can break it into u1 minus v1 times u1 plus v1 equal to m2 v2 square. This is second equation. Well, you can put the second equation up top and then divide by the first equation, and the m1 u1 minus v1 is cancelled out on the left, and m2 v2 is cancelled out on the right. So you have left is u1 plus v1 equal to v2. And you can eliminate v2 and find v1 by putting this back into equation 1. So if you put it in, you got m1 u1 minus v1 equal to m2 u1 plus v1. And finding the final velocity v1, you get m2 v1 plus m1 v1 equal to m1 u1 minus m2 u1. And the final velocity v1 is m1 minus m2 over m1 plus m2 u1. And this is a elastic collision. Now you can plug this value in to find v2 because v2 is u1 plus v1. And working your way out, you get v2 equal to 2m1 divided by m1 plus m2 u1. So after collision, the velocity is something like this. So we can think of this as the case of Mokatai. Well, if you take a look at along the road, Mokatai is quite at rest before the collision because she's moving across the road. She doesn't have any velocity along the road. But then the motorcycles is coming in with some speed and then they collide. Now, if the collision is elastic, okay, afterwards, the motorcycle will have the velocity v1, something like this. And Mokatai will have the velocity of v2 like this. So we have three situations. First, when the two objects have the same mass, m1 equal to m2. Now, if m1 equal to m2, you see that v1 is 0 and v2 is u1. So this happens in billiards and snooker all the time. If you take a look at the tournament, the white ball is collided to the red ball, and then after collision, the white ball is at rest and the red ball is moving with the same speed. So that is the perfectly elastic collision. Well, it appears usually when the two balls is collide head-on to each other, when the mass are equal. Now the second case is when the second mass is larger than the small mass, the colliding mass. Well, this is something like you running to the building or colliding with the brick wall. Okay. Some small mass. Oh, sorry. Quiz time. Okay. Let's discuss it again tomorrow. And I will just write another question. So Okay. Here's a quiz. Sorry about that. Let's do this and then you can leave when you finish. Hopefully, still in time. We have for about 15 minutes. Okay. So there are 6 questions here.